There's exceptional to that. I mean, try to sample from it.
All right, so on the board, I actually summarized the equation. I will go through this equation really quickly so you can actually get to the review questions. Okay. So here on the left, there's actually 4 sections. 1, 2, 3, and 4. 4 sections, okay. The first one for chapter 10 is all about concentration conversion. Okay, the question when it comes to typically is actually give you one concentration and next to calculate what's the corresponding concentration for the other concentration unit. Okay, so we'll go through a few questions like that. So by now you should know the definition of mole, definition of density, and then the molarity, normality, mole fraction, mass percent, and molarity. Okay, so you should know what is actual definition of those concentration terms. Then we talk about the delta H solution. Okay, so delta H solution was composed of 3 terms, but mainly the delta H solute and delta H mixing. Right? Delta H solute is always positive. Delta H mixing is always negative. Okay, so you should know that what it means by your delta H solution is positive or negative. Okay, so if you see this delta H solution is negative, that means your delta H mixing outweight delta H of your solute. Okay, so in the terms you are going to see in your question will be the hydration energy is actually outweighting your lattice energy. Okay. And this bottom one is just the opposite. Okay. Then we come to the solubility type questions. Okay, typically when we come back to certain species, right? Can you predict which one have better solubility? And the basic idea is actually like dissolved light, right? The hydrophilic like to dissolve in the hydrophilic. Okay. So how do you actually differentiate what is actually hydrophilic or hydrophobic? So in the hydrophilic molecule, typically see OH and NH. If you don't see those things, then very likely they are hydrophobic. Okay. And then you also need to know how the temperature and pressure is going to affect the solubility. Okay, so once you increase the temperature for your solid and liquid solute, the solubility will increase, but the gas will decrease. Okay. Pressure only has effect on the gas solubility. Okay, the higher the pressure, you push more gas into your solvent. Therefore, its solubility is going to increase. Here is going to, there's actually one equation, right? The Henry's law equation. The solubility of your gas C is going to equal to 100 constant K times the external pressure. Okay. And then very last one we talk about in chapter 10 is actually collective property, right? So you should know that when the effective solute concentration increase, then the vapor pressure percent point will decrease. The boiling point and then osmotic pressure will increase. Okay, you should remember all these equations, right? And one type of question you're going to see in the question is actually, I'll ask you, okay, if I give a certain concentration of certain solute, okay, which one is going to have highest or lowest vapor pressure, boiling point, freezing point, osmotic pressure, right? So for those type of questions, you can know how to calculate your effective concentration, which will be your Bangkok coefficient I times the concentration was provided, right? So you have a good idea how to judge the Bangkok coefficient of a molecule. Okay, so that's all the things that you should know for chapter 10. I went through very quickly, right? If you can follow me, it means you're actually in good shape. Okay, if you cannot, that means you need to actually watch the video. Okay. All right, so then we talk about the reaction rates. Okay, because right now we learn the how to define the concentrations, right? So now we start to actually learn how the concentration change over time. Okay, so that is actually the definition of rate. Okay, so for the rate, you should actually know how to calculate it. Okay, so I think in your homework, you've always been asked the consumption rate of reactant or formation rate of your product. Okay, so those are this, right? The things I just described, right? Consumption rate of your reactant, formation rate of your product. It's just the term that I highlight. It is not the rate of your reaction. To calculate the rate of your reaction, you can further divide those formation rate and consumption rate by its coefficient. Okay, so that's actually a very important thing that you should know. One key type of question for chapter 11 is actually, can you determine the reaction rate law? Okay, the rate law from experiments. Okay, typically you're going to see a table, give you the rate and the initial concentration of different reactions. Right. So to do this row divisions to figure out the exponents. Okay. And then after that, we actually tell you how to calculate the unit of K. Right. So on the board, write out the general equations. The unit of K can be calculated as molarity 1 minus N, where the N is the reaction orders. Okay. Times second to the negative 1 power. Okay, so let's for the integrative, for this for the differential rate law. And next one, we'll start to talk about the integrative rate law for single component reaction. Okay, it can be zeroth order, first order, and second order. Okay, so depending on the order that was given inside the questions, then you should actually use different equation. The key that you know is actually about the integrative rate law is if you see the keyword like how long it takes. Okay, and the concentration is certain number at certain time. Right? So once time has been shown in your questions, and that is actually the time you need to use the integrated level. Okay, so at the end of chapter 11, we start to talk about the activation energy EA. Okay, so the default equation you need to memorize EA is going to equal to the frequency factor A times exponential negative EA over RT. Okay, so EA is actually your activation energy, T, that's the temperature. Okay, and then if you see a question start to talk about two temperature, okay, so it's actually asking you like whether you know your reaction rate constant K is influenced by the temperature. Okay, so the equation I'm going to use is actually natural log K1 over K2 equals to B over R. Parenthesis 1 over T2 over minus 1 over T. Yes.
The second formula from the bottom.
Yeah.
K equals A times.
Oh yes. Sorry. Thank you. My bad. Okay, so the equation second from the bottom is K, okay, not EA. All right, that's all for the chapter 11. Okay. Chapter 12. Chapter 12, we start to talk about the equilibrium constant, right? At the beginning, we can actually tell you what is the equilibrium constant. Instead, we tell you what is chemical quotient Q, right? So chemical quotient Q is actually the things you can always calculate at any given time of the reaction. Right? All you can do is actually plug in the given concentration of your reaction and product. Okay. But reaction will come to an end, meaning it's going to reach equilibrium. Okay, only at that specific condition you can write out and express the equilibrium constant K using the same formula, right? Allows concentration as the concentration at equilibrium. Okay, and then one type of question you're going to encounter a lot in chapter 12 is actually to predict where the reaction is going to move to. Okay, so every time you write out the quotient, you can calculate a product over reactant. Right. So if your Q is larger than your K, that means actually at the current status, you have too much product. That means actually the reaction is moved to the reactant side, so that your Q eventually will equal to your K. Okay. On the other hand, if your Q is smaller than your K, it means actually your current status, doesn't have enough product compared to the equilibrium. Therefore, introduction move to the product side. Okay. So those are the first type of questions they need to know. Second, wherever the equilibrium constant K, you can either express in terms of concentration or pressure. Okay, so we use Kp to represent the equilibrium constant using pressure. Kc is actually using concentration. And these two are interconvertible. Okay, so the converting equation is actually the one I highlight here. Kp equals to Kc multiply RT to the delta n's power. Okay, and the delta n was calculated when you count the number of gas molecules or the mole of gas molecules on the product side minus the mole of gas molecule in the reaction side. Okay, and the R here, every time you see pressure, this term shows up in your equation. The R that you need to use will be 0.0820 ATM per liter. Okay, so those are the things that you should know. Okay, and then the very last things that you want to know for chapter 12 will be how to calculate the new K for the target equation. Okay, so all these equilibrium constant calculations, however you do, it will always reflect on the exponent side. Okay, if you flip the reactions, okay, the new equilibrium constant K will equal to the reciprocal of the original K. If you multiply factors, then those factors goes to an exponent. Okay, and if you add up two equations, then the equilibrium constant just multiplies. Okay, so that's all. Not much, right? So these are the things that you need to actually become really familiar with. Okay, before you actually goes into CASA. Okay, so with that being said, we're going to enter in our first questions. Okay, any questions before we get started? Everybody ready? Okay, so question number 1. Okay, we'll start from chapter 10. Determine the mass in gram of cycloheptane. Okay, let's give you the formula, give you the molecular weight. That must be added to 60.3 grams of benzene to make a 0.599 M solution. Okay, so what's the keyword here? What's the keyword? Okay, I just highlight this. So apparently it's actually about the concentrations, right? So eventually, you know, that is actually what you're looking for. The mass of gram of a certain species need to throw it into another thing, right? So when we get this sentence, A will be throwing to B to form a solution. A will be your solute, B will be your solvent. Is that clear? This is actually something to get used to. Okay, if I say the species is going to be added into the other species, okay, A is going to be added into B, then you actually know A is actually your solute, B is actually your solvent. Okay, so if you understand that, wherever your keyword, you know the thing you're actually trying to solve is actually the mass of your solute, right? Then you start to look at the data that you have. Then you know this is what the formula weight of your solute, right? Which is 98.2 grams per mole. That apparently is your solvent, right? So the mass of your solvent is 60.3 grams. Okay, and then this tell you the molarity of your solution is equals to 0.599 m, right? So those are all the information that you know. Okay. So where did you start? You start from the definition of concentration first. Here, the only concentration term that will provide is what? Molarity, right? So you know the molarity was defined as moles of your solute divided by the mass of your solvent in kilogram, right? Do you have this or do you have that? What do you have? Yes, you do have the mass of solvent, right? Therefore, you know you can at least plug in this, which is 60.3, that's gram, right? Into actually divide by 1,000. So it becomes kilogram. Okay. Do you have more of your solute? You don't, right? But do you know the definition of that? Yeah. So the mole of your solute was actually can be defined the mass of your solute divided by the formula weight of your solute, right? Do you know the formula weight of your solute? Which is 98.2, right? So you know you can write the things. And you also know the overall concentration is equal to 0.599, right? Therefore, you conclude this equation. Well, the only unknown that you have is the mass of your solute. Then all you do is actually just solve this equation. Okay, so the mass of your solute will equals to 0.599. I first multiply this on both sides, right? So there will be 60.3 divided by 1,000. And then I multiply 98.2 on both sides. And then once you finish that, you should be able to get a number of 3.55 gram. Okay. So let's take how you solve this question number 1. Okay, so let's a quick recap. Okay, so how do I solve this one? First, essentially, I already know what I might solve, what I might solve it. Right, that's always needed. Okay, you need to be very clear about it, you know, who is the solute, who is the solvent. Okay, and then from the data that you know, what you can have is actually the formula weight of your solute, mass of your solvent, right? And then you know the concentration is molarity. Then you're starting from the definition of molarity, trying to put in all the information that you know. Okay, you also need to know the definition of mole was calculated by the mass of your solute divided by the formula weight of your solute. Okay, then you can come to the specific equation. Then after that, will be solving the equation here by your multiple. Okay, so it should be actually very straightforward, a very basic type of questions. Okay. Okay, any questions for this? We good? Okay, number 2. Calculate the vapor pressure in torque at 310 K in a solution prepared by dissolving 37.63 grams of non-volatile, non-electrolyte sucrose in 129.7 grams of water. The vapor pressure of water is 310, at that temperature is 47.08 torr. Okay. What's the keyword? What's the keyword? Yes, vapor pressure. Okay. every time you see the vapor pressure, you know it's collective property, right? So everybody still have your screenshot? Okay, zoom in and go to the collective property section. Then you will see there's only one equation you can actually use, and that's your plane. Okay, so the things you want to solve is what? Okay, so keyword is of course the vapor pressure. Okay. So you want to actually calculate the vapor pressure in torr, right? What's the data that you have? Temperature is 310, right? And then dissolving this in lead, okay? What's your solution? Sucrose is the solution of the solid. Very good. So, you know, the mass of your solute is 37.63 grams. Formula weight is 342.3 grams per mole. And then you know the mass of your solvent is 129.7 grams. Okay, what else do we know? Okay, the vapor pressure of your water, okay, which is your solvent, right? It's going to equals to 47.08. Okay. So that's all the things that you know, right? And then if you actually go back down to the things I just showed you previously, right? How do we calculate? How do we calculate the vapor pressure? I'll just write here at the plane. We know the vapor pressure is going to equal to a mole fraction of what? Your solvent times the solvent vapor pressure. Right? So if you look at the equation I gave you today, if you go back to that slide, you'll see that's actually the equation they're going to use, right? So the things apparently you need to calculate is this guy, right? And that is the things you want to calculate. That means you actually know the mole fraction of your solvent and also the vapor pressure of pure solvent. Okay. So I will just write this so it's consistent. This guy was actually given. Okay. Then you actually calculate the mole fraction of your solvent. Right. So how do you calculate the mole fraction? So you know the mole fraction of your solvent will be the mole of your solvent divided by the total mole, right? Mole of your solute plus your mole of your solvent. Okay, and then you know that to calculate the mole of your solute will be the mass of your solute divided by the formula weight of your solute. The mass of your solute is actually 37.63. Formula weight is actually 342.3. Right. So if you do like calculations, you should be able to get a number of 0.11, right? Mole of your solvent. The mass of your solvent is 129.7. What's the formula weight of your solvent? Yeah, so can you actually calculate the formula weight by yourself in water? Okay, so if you can, then it's, just use 18 here. Then I give you a number of 7.21. Therefore, these things can be calculated as 7.21 divided by 0.11 plus 7.21. That give you a value of 0.985. Right? Once you get this, then you put it back in here, 0.985 times the 47.08. Then you're going to get a value of 46.374. Okay. So recap. When we read this question, first you need to know the keyword is vapor pressure. Therefore, you know it is collective property. Okay. Therefore, you know the equation you want to use is the vapor pressure equals to a mole fraction of the solvent times the vapor pressure of your pure solvent. Okay. And then you will realize that the only thing that wasn't given is actually your mole fraction. Okay. So if you know the definition of mole fraction, which is mole of your solvent divided by the total mole of your solution. Okay. If you know how to calculate that, then you'll be able to figure out the mole fraction of the solvent and just plug into the equation and get the answer. All right, so let's actually the large flow for question number 2. Number 3. Consider the solution. Okay, you got a lot of different types of solution now. It asks you which one has the highest osmotic pressure, lowest vapor pressure, highest boiling point. Okay, so those are keywords, right? Because once you think is boiling point, melting point, osmotic pressure, it has to be a collective property of questions. Right? So the things that you have to actually know is what is actually the effective concentration, right? So Q is you want to know who has the highest osmotic pressure, lowest vapor pressure, and highest boiling point. Okay, so if you look at these three things, okay. So we know when the concentration of your solute gets higher, your osmotic pressure becomes higher, right? And then your boiling point becomes higher. Therefore, this two actually is looking for the one with largest effective concentration, right? So that's actually something that you should know. Okay. And then for the lowest vapor pressure, okay, is also the one that requires you have the highest effective concentration, right? Because vapor pressure lowering, right? The higher effective concentration that you have, you're going to have the lowest vapor pressure. Okay. Therefore, all these three things actually looking for the same thing. The solution with the largest effective concentration. Right. Then you need to know what is actually effective concentration. It's basically this, right? Your Van-Hoff coefficient multiply the given concentration. Okay, so whoever is actually the largest, then it will be the answer for the three specific questions. Okay, then we look at our data. The first one is 0.04 m urea. Second is actually 0.04 m AgNO3. And the last one is 0.04 m CaCO2. Right? So if you look at these three, molarity-wise, they are exactly the same, right? Okay, that means actually this term is actually all the same. Then all you have to know is actually whoever has the largest I, then they will be your answer. Okay, So what's I for the urea? Okay, I hope that you see these things. Okay. So every time you see a species that doesn't contain metals, okay, there's high chance it is a non-electrolyte, meaning the I is going to equal to 1. Okay. Our second one, AgNO3. Okay, I equals to 2, right? So you know this one becomes Ag plus NO3 minus. So the reason it is 2 is because one AgNO3 molecule, they produce one Ag plus and one NO3 minus. Okay, so you produce 2 charged species. Okay, therefore I is going to equal to 2. Okay, and then your CaCl2, I will equal to 3. Okay, because you know this will become 1 Ca2 plus 2 Cl minus. So totally you have 3 charged species. Okay, so your I is equal to 3. Okay. So then, since you know all these 3 is looking for the solution that gives you the highest effective concentration. Therefore, you know the answer for all 3 would simply be CaCl2. Okay. Any questions for this? It's because the 2 intermolecular chloride. So the total number of charged species, is your vector coefficient. It is not a charge itself. It is actually a coefficient in form of your charge species. If you're adding up, that's your vector coefficient. Because it is an organic compound, it doesn't produce charged species that actually dissolve. Yes, every time you have an organic compound, I is equal to 1. Okay. Any other questions? I guarantee you're going to see this type of questions that you don't need to. Guarantee. So you better know how to calculate your I. We good? Okay. Number 4, tin chloride dissolved in water according to these specific reactions. What is the boiling point of the solution when 0.2005 gram of tin chloride is dissolved in 10 gram of H2O? The Kb of water is the specific number. Okay, what's the keyword? Louder. Boiling point, right? Again, boiling point, electric property. Only one equation that you can use, right? Delta T equals to I times K, I times K times UN. Okay, so that's all the things that you are looking for. Okay, so Q is that you want to know the new boiling point, right? Data that you have your, okay, let's say you have that much of tin chloride, right? Tin chloride is your solar solute. The mass of your solute is 0.2605 gram. Formula weight of your solute is 260.5. grams per mole. Okay. And then the mass of your solvent, which is your water, right, is 10 grams. Then your Kb is 0.512 degrees C per molarity. So those are things that you know. Okay. Okay, so plan. You should know that the only equation that you have here is this. Right? The change of your boiling point can be calculated using this specific equation. The vector for the I times your Kb times the molarity of your solution. What's your I? Okay, I hope you can see that now. The differential equations, right? Because you have 1 SM4 plus and 4 CL minus 1 plus 4 give you the value of 5. Okay? You have your Kb already, right? Therefore, you only need to compute your molarity, right? Definition of molarity will be moles of your solute over mass of your solvent in kilogram, right? Mole of solute can be calculated by mass of your solute divided by the formula weight, right? So it will be 0.2605 divided by 260.5. That's a mole of your solute, right? Mass of your solvent will be 10 grams. Try to convert it into kilogram. So that's what you do. And this will give you a concentration of 0.1. Therefore, you know the change of your boiling point will equals to 5 times Kb, 0.512 times concentration 0.1. Let's give you a number of 0.256 degrees C. Okay, so that is the change of the boiling point, right? But the question actually is actually what is actually your new boiling point? Okay, we know boiling point elevation, so it will be actually your normal boiling point plus the change of boiling point. Normal boiling point is 100 degrees C plus 0.256. Therefore, your answer will be 100.256 degrees C. Okay, so recap again. Keywords, boiling point. Therefore, you know the equation you're going to use is delta TB equals I times K times N. Okay, and then start to list out the information that was provided. Okay, so you list out all the mass of your solute, formula of your solute, mass of your solvent, and your Ke, right? And then based on the equation given, you should be able to figure your I equals to I. Okay, and just plug in all the terms that you have. Okay, then you can calculate what your delta TB value is. Okay, and be careful, here it's not actually about the change of your boiling point. Instead, it's actually about the new boiling point. Therefore, it actually is 100 plus the change of the boiling point to get your final answer. Okay, so that is how you solve question number 4. Right. Okay. Any questions for this? Yes. The one. No more boiling point. Yeah. Yes. And you guys also noticed that I went faster than usual, right? Because we only have 2 lectures, but that's actually 9 questions we have to go through, right? So my idea is that if I go fast, at least you can go back and watch the video. Okay, so, but if you have questions, you want to actually understand the things right now, that's fine. Just raise your hand. I will actually slow down for you. Okay. Question number 5. When 5.6 gram of unknown non-electrolyte is dissolved in 50 gram of acetone, the boiling point increased by 3.8 degrees. If the Kb is let numbers, calculate the molar mass of this unknown solution. Okay, what's the key word? Boiling point, right? Boiling point is still be the key word. Okay, so since boiling point is your key word, you have to use exactly the same equation that we used in the previous question, right? Delta TB equals to I times K times N. That's the O2 equation. Okay, so but the things we want to solve here is different, right? Because we want to know the molar mass. So the formula weight of your solute, right? That's the things we want to know. Okay. So once you know what you're actually looking for, then start to write down the things, right? So you know the mass of your solute is 5.66 gram. Okay. Mass of your solvent is 50.0 gram. And then the delta TB is 3.8 degrees C. The K is 1.71 degree per molarity. So these are all the things that you have. Okay. Therefore, we can start, okay? Because we know the delta TB is calculated from I times K times M. Okay. Do you have your delta TB? Yes, right. So the change of your boiling point is 3.8. Do you have your I? What's your I? How do you know it's 1? Very good. So I is equal to 1, right? Simply because it says this, right? This tells you your I equals to 1. Do you have your K? Right here, right? 1.71. Do you have your N? You don't. Okay. But we do know the definition of M is mole of your solute divided by mass of your solvent, right? So do you have the mole information? You don't, but you do have the mass of your solvent, right? The mass of your solvent is 50, right? But want to convert it into kilogram. Okay. So up to this point, you can calculate the mole of your solute already, right? So if you do the calculation, you can know the mole of your solute is 0.111. Okay. Then you also understand the mole of solute is actually the mass of your solute divided by the formula weight of your solute. Therefore, you know to calculate the formula weight of your solute, which is what you're looking for, right? It simply equals to the mass of your solute divided by 0.111, which is 5.66 divided by 0.111. Therefore, you can get the number, the formula weight of your solute equals to 51. Okay. So let's see how you solve question number 5. Yes. So degree C and K, right? So the only difference between the two is that the K, the conversion is just a specific constant. Right, you add 273 to convert your C to K. Okay, but it doesn't really matter here because the change 1K is actually the same as change of 1 degree C. So they are actually equivalent. Any other questions? Good question though. Okay, I wish I can go through 2 to 3 more questions today. Okay. So question number 6. calculate the molarity of an aqueous solution that is 8.1% by mass, you might need to know the density is 1.1 gram per ml. Okay, so what's the keyword here? What's the keyword? And 8.1% by mass, right? The mass percent. So you've seen two concentration terms, right? So this is a standard for all my chemistry for concentration conversion calculations. Okay. So once you know that, then you should know what's the things you want to calculate, right? That's the things you want to calculate. Molarity, right? Which was defined as mole of your solute volume in liters, right? Of the solution, right? So that's the thing that you will need. Data, you have mass percent, right? It is the mass percent is equals to 8.1%. Okay. And then the solute is calcium chloride, right? And then the density is 1.10 gram per ml. Okay. So here, when you write out your solute, you should also know the formula weight of calcium chloride. This is actually the one you actually use your periodic table to calculate it. Okay. Then this will give you a number of so those are the information you was provided. Okay. So every time you encounter this concentration conversion type of questions, right, you always need to make assumption. And the assumption based idea is that you want to make the denominator equal to 1 or 100, right? So the only time you need to assume 100 is that if you see the percent, which is the case that we're getting now. Okay. So we want to assume that the mass of your solute plus the mass of your solvent equals to 100 gram. Okay, so we want to do this simple because your mass percent is defined as the mass of your solute divided by mass of your solute and solvent multiply 100, right? So that from these two relationship, you can see that you can easily compute that the mass of your solute will equal to 8.1 gram. Mass of your solvent is equal to 100 minus 8.1, which is actually 91.9 gram. Okay, so once you make the proper assumption, then you can get this information out immediately, right? So once you have this, then you look back the things that you need is here, right? First, you need the mole of your solute, right? And then we know the mole of your solute can be computed by the mass of the solute divided by the formula weight, right? Therefore, you can compute that first. Mole of your solute is going to equal to the mass of your solute, which is 8.1, divided by the formula weight, 110.98. They will give you a number of 0.073. Okay. The next thing to calculate is actually the volume of your solution, right? So here, every time you see the concentration conversion involve molarity, you must use density information. Okay, so here's actually the things how you should get the B. Okay, because we know the density was defined by the mass over volume. Therefore, you should know that the volume can be computed by the mass of your solution divided by the density of your solution. Okay, so what's the mass of your solution? What's the mass of your solution? 100. And then density is 1.10. Therefore, you know the volume is going to equals to 90.9 milliliters, which will make it equal to 0.0909 liters. Okay, so once you have this, once you have that, you can just plug back into this, right? So it will be 0.073 over 0.0909. Then you can get a number of 0.803. That's how you get to the answer. Okay. So recap this quickly. When we see two concentration terms, it's a standard concentration conversion type of question, right? So for these type of questions, then you always need to make assumption. Okay, that's where how you get started. Okay, so in this case, we assume U plus MV equals to 100. Then we can compute what's the mass of the solute, what's the mass of the solid. Okay, and because this one actually involves the conversion into the molarity, therefore you get the molar information using the density. Okay, so if you plug in all these things, follow the proper logic, then there shouldn't be any problem to get the correct answer quickly. Okay. Question number 7. KBr does not dissolve well in nonpolar solvent. Okay, because, okay, so this is like an interesting question. Okay, it's more like conceptual type of question, but student actually doesn't understand why this is such a case. Okay, so this actually go back to the things we said, delta H solution involve two parts, right? One is actually three parts, delta H solute plus delta H solvent plus delta H mixing. Okay, so delta H solute means actually to actually break these things apart, right? So let's actually where we see this lattice energy term comes in. Okay, and it's always positive. The other one is actually the delta H mixing, which is actually interaction between the solute and the solvent molecule. Okay, and that one is always negative. Okay, so the KBr, okay, KBr is a electrolyte. Everybody can see why KBr is electrolyte. K is actually the 1A element, right? Okay, so every time you see a compound have this 1A element, consider it as an electrolyte. It means that once you will actually dissolve and forming this charged species. Okay. And then the solvent that you have here is a nonpolar solvent. Okay, so we talk about it as like dissolve like. Okay, so for your nonpolar solvent means it doesn't really like this charged species. Charge is actually a polar type of things. Okay. So in this actually, when you put these two things together, the interaction between your solute and solvent is not going to be a favorable process. Okay. So they have actually many multiple choice, but they're not giving me all the options. They're not giving me the answer. Okay. So let's actually only finish off. It says the solute interaction. Okay, solute interaction actually is the same as this term. Okay, lattice energy. Okay, so they like each other. Okay, it's much stronger than the solvent or solvent-solute interaction. This is actually a term that matters. Okay, so solvent-solute interaction. This is actually your hydration energy. Okay. So typically you will need to have a stronger hydration energy, meaning that if you're more comfortable more comfortable when the solute dissolve inside your solid. Okay, then you form a solution. Okay, but because here it's different case. Okay, the solute actually like itself more. Okay, therefore it doesn't want to get dissolved. Therefore, the solubility is actually poor. Okay, so this actually fortunately connect the delta H solution. Okay, so you will see some variant of these type of questions. I want to see is that if you want to actually form a solution, your delta H mixing or the hydration energy term must be the dominant term so that it will dissolve well. Okay, so this is the concept that you should have from this type of questions. And that's all for the chapter 10. Okay, we're entering chapter 11. This part will be the very last portion we'll go through today. So from here, you can clearly see that's actually a table, right? So you know it's actually the question asks you the reaction orders. Okay. So let's read this question quickly. Let's say you have a reaction 2ICl plus H2 give you 2I2 plus 2HCl. And then the following is actually the experimental data. Asks you what is actually all reaction order. Okay. So once you see this table, then you know differential rate law is actually the things that you want to have. Okay. So question. Overall reaction order. Okay. And then you should know that when you write out your rate law for this specific reaction, you will have this form, right? Rate is going to equal rate constant K times your reactant. Okay. You should definitely know the reactant that you have here is actually ICl. Let's say to the X power. H2 to the Y power, right? That's actually the things you have to write out by yourself. The rate equals rate constant K times reactant to certain power, right? And the reactant, you should be able to read it yourself from the equation, right? That means the two species on the left are your reactants. Therefore, you know this will be the differential rate law you're going to use. Okay? Data, right? So you have three rows. Then you should actually use those three rows to write out the equations for your differential rate law. Okay, so experiment number 1, initial rate is 3.7 times 10 to the negative 7 equals to rate constant K times ICl concentration 1.5 to the X power, 1.5 to the Y power for your H2. Then repeat the same process for the second and third equations. Okay, which is 115 times 10 to the negative 7 equals to K times 3 to the X, 1.5 to the Y, and then 134 times 10 to the negative 7 equals to K times 3 to the X, 4.5 to the Y. Okay. So the main goal is actually you're going to do this raw integration to figure out your X and figure out your Y. And then the X plus Y give you the overall order. Okay. So let's say I want to figure out solve my X first, right? So to solve your X, what you need to do is actually to choose two equations that the concentration for the species where you can solve your Y, okay, they are actually the same. Okay. So if you have that concept in mind, then you know the two equations you want to pick is the 1 and 2, right? Because your first, the concentration of your first component is different, but second one is the same. so that you can just solve for your x. Okay, so we do 2 divided by 1. So this divided by that, you're going to give a value of 4. Okay, you got a number of 4.05. A divided by k give you a value of 1. 3 divided by 1.5 give you a value of 2 to the x power. 1.5 divided by 1.5. That's 1 to the y power, right? So since the base of this term is actually 1, so the whole thing actually gives you a value of 1. Therefore, you know the equation becomes 2 to the x power equals to 4.05. Therefore, you know that x will equal to 2. Right. So once you have that, you want to solve for your y. Then you actually use the equation where the concentration associated with y, they are different. Therefore, you know equation number 3 and equation number 2 is actually things that you need to do. So you do 3 over 2. Once you do the divisions, you got 8.93 equal to a divided by k is 1, right? 3 divided by 3 is also 1 to the second power times 4.5 divided by 1.5, that gives you a value of 3 to the y's power. Okay. And then here 8.93, okay, can be approximated into 9. Okay, so like here, we actually approximate this one into 4 so that we get the exponent of 2 for your x. Okay, so once you have this, you know you can solve 3 to the y's power equals to 9. Therefore, your y also equals to 2. Therefore, you know your reaction rate is going to equal to rate constant K times ICL seconds power H2 seconds power overall will equals to 2 plus 2. It's fourth order reaction. Okay. So any question for this? Now, you can see all this information on the recording. Okay, and then you have all the things for your hangout. Okay. Before we leave, let's look at one more thing I want to add to this question. So right now you know how to solve your x, solve your y, right? The other question that we can follow up with this is, can you calculate your k? Okay, so the way you calculate your k is actually you pick a rule. You right now you know your x, you know your y, right? And then you know your rate, you know your concentration. Then you can calculate your k. Okay, so those are the questions you will encounter for this one question. That's it for today. Thank you.
Only question I can hear.